All right, so let's get started. So thank you for being here that early in the morning. I know it's always hard. Also for me, it's a little bit hard to be here that early. But let's try to make this fun. So in the next around like 1 hour, I'd like to give you a brief introduction about what virtual threads are used for in Java 21 and how you can use them really easy in your application to make your application much faster. So, short introduction to myself. My name is Christian. I've been working as a software engineer for like the last 15 years. Started with Java 6 back then switched over around 7 years ago to more of a full stack role where currently I'm coding with TypeScript, JavaScript, and Java on a daily basis. I also do some trainings on the side, and yeah, I really like to speak about different topics at conferences, and I also do some stuff on YouTube where I talk about like advanced TypeScript stuff. And you can find everything I will talk about today on my website, type.rocks, and there you also find the GitHub, and you also find my LinkedIn and everything to my YouTube channel and so on. So when you want to stay in contact, just visit the website. Now, if you have questions, you can ask them all the time. You can just go to type.rocks/QA. There will be then a redirect to a website where you can just answer a question. When we don't have enough time at the end of the talk, I will answer the questions later. But of course, when we have time left at the end of the talk, just ask them right away. So what will be the topics we will talk about? We will talk about like 3 different topics here. So we will build a Spring Boot application. And first we will build them in a blocking approach. Then we will switch over to it being reactive. And then we will migrate it to using Project Loom and virtual threads. So first, the blocking approach. So when we started, like in the early days, we only had the possibility to use the blocking approach. So for example, we have a REST template. When we make an HTTP request, then the thread will block. And many of us maybe are still using it to this day, because I'm also still using it mainly because often you don't have applications which need that high of a throughput. You have like, for example, it's an internal application which has maybe 100 users a day. And if you only have like a simple CRUD application, then you don't need it to be like reactive and have this additional overhead of reactivity. Now, because of that, let's build this blocking application. So we will go into IntelliJ, and what I'm currently having here is just an empty application, which has just POM XML, which is on version 3.1, and I'm currently on version Java 22, but of course you can also do this with Java 21. So what we first will do is we will just create a new controller, like this, and now what we will build here is we will have like an API where we can access the speakers of the conference, but I will not have the real speakers because then I would have to call like an HTTP endpoint, and sometimes the Wi-Fi isn't really working, so I will create a fake one. So let's have our REST controller here, and we have a request mapping like this. And the first thing we will say is we have our get mapping, where we say we have our speakers here. Now, what will this return? It will give you a list of speaker, and we say get speakers here. Now, let's create this speaker record, and we'll keep this really easy. So we will just say this has just a name. So, and now let's import this. Now, to fake this HTTP request so that we can send some fake REST API call, I will create a service. So we have here an auto-wired private fake HTTP service. And let's build this. And we will keep this really simple as well. We will just say this is a service here. And we will then say here in the get speakers, we call fake HTTP service, retrieve speakers, like this. And what we now can do in here is, we have, of course, to return this here. The first thing we will do here is, we will say we have a thread.sleep of 1,000 milliseconds, because this basically is what happens when we call an endpoint in a blocking manner. The thread will block until the response comes back from our endpoint. So let's just say we have here a sneaky throws so that we do not have to handle this. And now we have to create our speaker list. So we have our private final list of speaker. And this is the speaker list. And we will create like a small one with 10 speakers in there. and we will say map to object, and for each of these integers we will create a new speaker and have the speaker like this. So what we then will do is we will just return this speaker list. Now this is everything we need to do to make our application running. So what we did is we created an endpoint and we just call this retrieve speakers, which fakes this blocking API request. So let's run this. And what we now can do is we can open JMeter. JMeter is like an application to performance check your application. And we will keep this really easy. We will say we want to have 1,000 concurrent users to access this application. We have a ramp-up time of 10 seconds, so we will only start checking the performance after the initial 10 seconds, and we will do this for 20 seconds all in all. So let's run this here, and let's see, we have the API/speakers in there. So when we run this, we can see here the 1,000 threads get created, and then it starts accessing our endpoint. And what we now will check is what will be the performance of this endpoint when a huge amount of users access our endpoint, because we don't have 1,000 threads available in our endpoint currently. So let's see what happens here. So we have 20 seconds over, and we can see here it's quite slow, because we can see here it starts with over 2 seconds of time needed for the first request, and at last it needs almost 5 seconds. Now, why is this? Well, the problem is that in Java, for each of these platform threads, for each of these normal threads which get created when you, for example, call a new thread, it will create an operating system thread. And an operating system thread is quite expensive, and this is why Tomcat, or any server basically which is used, for example, in Spring or in other frameworks, has a thread pool which reuses these threads. And so let's create some threads and let's see what the issue here is. So we will go back into IntelliJ, and I have here a test which I can use. And this test has the sleep method in it, just so that I can wrap my thread.sleep so that I don't have to handle the checked exception. Now let's create this test here, and we have the test. And what we will do is we will create 1,000 threads to start with. So we say we have a list of threads, and we have this thread list, and we say in stream range of 0 to 1,000, so we will create 1,000 threads. And we could do this now with new thread like this, but in Java 21 there is now a new way of doing this. We can say thread.offPlatform, and what this does is basically the same like new thread, but the only difference is it will make it easier for us to just switch one thing later. So we say we want an unstarted thread, something which is not running, and we will then say we have a sleep of 20 seconds. So what this will do when this thread gets executed, it will just just sleep for 20 seconds, and then it will be done. So we can say threadlist.forEach. So let's start each thread. And then, of course, you have to wait until these threads are done. So what we will say is threadlist4, and we'll then say thread.join. So we wait until each thread is done with its work. So what I now can do is I will now open the terminal, and I have here a function, a little script which I can use, count threads from Java. What this does is it basically just checks how many threads on the operating system level were started from the JDK, or from a Java process. So I will now watch these threads here, and let's now start these 1,000 threads. So let's start them. And what we will see is that we here now have 1,000 more operating system threads. And this is exactly what I mentioned, that for each Java thread, a thread on the operating system gets created. So let's now stop this, and we can see the threads will go away again. Now, what's the problem with this? Well, when I change this to, for example, 1 million threads, and I rerun this, we will see in just like 1 or 2 seconds that we get an out-of-memory exception. Because, let's stop this here, we can see here, unable to create native thread, out of memory error. And when we check here, we can see, for example, stack size of 2 megabytes to 2,000 kilobytes, and the thread 4,000 could not be created. Now, this is exactly why we can't just create more threads. Because when we have a stack size of 2 megabyte, or for example also 1 megabyte in certain cases, because you can change the stack size if you want, then it would take to have like 1 million threads, you would need 1 terabyte of memory. And this would be way too expensive to be able to do for like just one application. But we would need 1 million threads to have a CPU usage of 100%. But why do maybe you think, well, what is this CPU usage of 100%? Why do we need 1 million threads? Well, when we check what the thread is mainly doing is it's mainly waiting. Because when we think of, let's say you have only one thread in your application. As soon as a request comes in, the thread will handle this request. And then, for example, in our case, it will call this fake API. But everything between that, when it calls the API and before the result comes back, the thread is just waiting. So in this time, when the CPU hasn't something to do, then it will just wait. So the real usage of CPU on a thread is really, really small. So that's why we need to have a huge amount of threads to be able to really keep our CPU busy. So we were here in these early days when we said, well, this is nice because it's fast enough in our cases. But then we went to, well, we need more threads to be able to handle these throughputs we have. So we then went back and went, well, how can we fix this? Because we can't just have more threads, we need to change this somehow. So, and this is where we switched over at Java 8 to being able to use reactive, also with streams, of course, but also with like things like completable future. And let's now see how we can make our application much faster by using reactivity. So we go in there, and let's go back here to our main controller. And we will create a new endpoint here, a get mapping here, and we'll say /speakers async. And what we now will do is, instead of returning a list of speakers, we return a completable future list of speaker. And I will use here the Java approach from the JDK. Of course, you could use like Project Reactor or like Vertex or RxJava, but this is like baked in for any framework you use, for example, for Quarkus or other stuff. So I will use this one. And let's say we have get speakers async. Now we will call fake HTTP service retrieve speakers async. Now, of course, we have to create this first. Now, we can see here we need to return a list of completable future list. Now, what we can't do is we can't say thread.sleep, because the problem with this is that thread sleep is not reactive, so this will also block the thread, so we don't want to have this. So we need to say return completable future supply async. So we say here we want to like basically create a completable future and supply it with this speaker list, but we need to add this delay we had. So we need to add a delayed executor like this, which enables us to say basically the same thing we did with the thread sleep, but in a non-blocking manner. So we say here again we want to wait 1,000 milliseconds. And now we have basically the same as we have with this retrieve speakers. So we fake the delay of getting a response. For example, in our case, it would be when you use Spring like a web client where you wait for this response, but in a non-blocking manner. So let's now go back into our controller here. We can see everything compiles. And now let's rerun this application. And we will now go back into JMeter, and let's remove everything we've collected so far. And now I switch it to using speakers async. Now let's run this. And what we now will do is, again, just call our speakers async endpoint, but with the one difference that we will call this in a non-blocking manner. So what should happen is when we call our speakers async endpoint, as soon as our thread will block, it will be freed to be used by another thread. So we can see here 20 seconds are over, and let's now see what the response here is. And we can see it takes 1 second for all the calls, because this is basically what we would have expected, because this takes these 200 threads, but as soon as something blocks, it will be freed to do something else. And this is the huge improvement with completable futures or with reactive programming. But the problem here, of course, is, which we'll see later, that it's a little bit more complex, but just for you to keep in mind, if you can't use Java 21, maybe some of you can't use Java 21 because you are still stuck with earlier versions. And when you have problems using then the blocking approach because it's too slow, maybe give this completable future here a try, because when you have like simple endpoints, it's really easy to make this really, really much faster. Now, but the problem is that, let's go back here. We were here in, we say that we were in the early days. We say, well, this is really fast, it's really nice to use. Now, the problem is, what we discovered later is we also need simplicity and easy to use and easy to read code. So what do I mean with this? Let me show you how we can make things a little bit more complex. Let's say we want to have for each of the speaker his talk. So for the sake of simplicity, we will just say we have one talk per speaker. Now, let's say we have this here for our blocking approach. We say we have /talks, and we have a list of talk, and we say get talks here. Now, after we've created this record here of talk, we will just say this has a speaker in there to keep it really easy. And now what we need to do first, of course, is we have to get all the speakers. So we say fake HTTP service, retrieve speakers. Now, for each of the speakers, we call map, and then what we do is for each of them, we will call a new method we will create. So retrieve talk, and we pass in our speaker. Now, what will this retrieve talk do here? Let's create this. This will return a talk, and we will say here thread.sleep of 500 milliseconds, so a little bit shorter, and we'll say return new talk, where we pass in the speaker. Now, the problem with this approach is that when we go back here, we can see that this, even if this will not block at all, this will take 6 seconds for each request, because this one takes 1 second, and this one takes 10 times 500 milliseconds, which is 5 seconds in our case. Now, of course, you maybe say we could change this to parallel stream, but you have to always think about that parallel streams work on also work on a thread pool, and this thread pool is the size of your amount of cores you have in your application minus 1. So, for example, in my case, I think I have 10 cores in there. Then it would only have a parallelism of 9 threads. So this is also, of course, this would make it in this case faster, but if you have like 100 speakers like we have here at the conference, then this would just not be as fast as it could be. But we can see here it's basically easy to understand what the code does. We could make this even shorter by using a method reference here, but I will leave this. So what's the problem when we change this to make it non-blocking? So we have our talks async like this, and we have a list of talk. But now what we need to do is we need to wrap this in a completable future list of talks, and we say get talks async like this. And now it gets a little bit more complicating because we are not allowed to break this chain of reactivity. So what we need to do is we have our final var speaker future in this case, and we say fake HTTP service retrieve speakers async. And now we need to also map over these speakers, but in a different manner. We need to say return speaker future. And then, of course, we can see here we have so many different options to use when we want to map over our completable future. So it's really hard to really know what it does, because we can see basically everything here returns the same as we pass in here. So it's really hard. Everything here returns this completable future. Now, in our case, we use then apply async. Not async here. And what this will do is it will take the response here we get back as soon as we get it, the speakers here, which is a list of speakers. And what we then will do is we have to map over this like we did here in our speakers. So we say here we have our final var talk futures, and we say speakers.map. And what we then will say is for each of the speaker, we will say fake HTTP service retrieve talk async, because we also need to do this asynchronously, because if we do this blocking, then it will still block again in our call. So let's just say here we have a tool list, and let's create this method here. So this, of course, will also again return a completable future of talk. Now we can just copy this from up here from the supply async. You can just copy this here, and put this down there. And the only thing we need to change is, of course, we don't need to return a list of speakers, but we need to return a talk. Basically the same as we did here. We pass in the speaker, and of course, these are 500 milliseconds instead. So now, but when we now say return talk futures, we will see that we get an error. When we say talk futures, we will see this does not work. Well, why is this? And this is like another thing which is really complicating with reactive stuff. Because this here, when we check, when we get the real type, we can see this is a list of completable futures of talk. So what we really need is, we need this the other way around. We need to have this in one completable future. So what we have to do here, additionally, is we have to say return talk futures map. We have our completable future join here because we want to wait until all the completable futures are done. And then we use toList here. And in this case now we can see that our code now compiles. Now I will not run this in JMeter, but of course this will be much faster. It will be like 1.5 seconds. But when we compare these two, this is much more complex, and it also has so much more boilerplate code around it. So what are the problems with this reactive approach? The problem is, in my opinion, it's hard to write. And I also, like, as mentioned, I work like since 8-9 years. I also work as heavily with JavaScript and TypeScript, and we also have there, of course, only like we work with asynchronous code heavily. But even there, we switched over to using like this async await approach, so that we don't have to wrap everything like in this callbacks or in this promise then blocks, because it's really hard to understand these wrapped code constructs. It's also hard, of course, to write it, but maybe you can do this, but sometimes later you have to read your code again. And this is really hard to do because it has like a steep learning curve, because you have many different frameworks you can use. So every framework has its own functions, every framework has its own like ways of handling things. And it's also really hard to test the code, because the business code almost gets like secondary when we code with reactive code, because you have to wrap basically your code to make it like synchronous again in your tests, so that you can really test your code. And last but not least, it's also like the compatibility. When you need to have reactivity from the first part until the database to really keep this in a reactive flow. So you need to have like R2DBC connections. You also have different frameworks, different implementations you need to use. So it's really hard, in my opinion. So we went now from like the early days of reactive to say, well, this is cool, this is fast, but now we are later back here, we say, well, this is way too complex. Because they went back and they were thinking, okay, well, what was the problem, why we went away from this blocking approach? And this is where they started to look into Project Loom, like 2019, and back then it was also called Project Fiber. And they were thinking, well, we need more threads, basically. We need to make sure that our CPU is always working. And the problem why we went away from this blocking approach is that we couldn't afford more threads. So they checked how many threads do we really need or want, and they said, well, we need 1 million threads, basically, to be as fast as reactive programming. Because when we have a CPU usage of less than 100%, reactive programming will always be fast, because it can ensure that when we have enough traffic, that really the CPU usage is as high as possible. So, and they went on and they found a solution, the virtual threads. So to keep it simple, what are virtual threads? The important thing to understand is that virtual threads are only a Java construct. Like, they only exist in the JVM, like in the JDK itself. So we have then the platform threads, which are, when you nowadays read from platform threads in Java, these are like these legacy threads, these normal threads where when you create one, it creates an operating system thread. Now, let me show you how they work. So we have here our virtual thread, and the important part is how they work is, let's say we have our speaker example, and a request comes into our /speaker endpoint. The Tomcat, so the server which is running, will create with its executor service a new virtual thread, because virtual threads should not be pooled. Virtual threads are like single units of work. They get created and then thrown away as soon as you are done with them and as soon as they have done their work. Now, the virtual thread, as soon as it gets created, it looks for a worker thread. Now, the worker thread we can see here, these are platform threads, and they are connected, of course, with the operating system. Now, the virtual thread looks for one of these worker threads in a pool, because the worker threads are not just like in the hundreds, but they have like a fixed pool size of at most like 40 threads, because mostly these are enough for the virtual threads. So the request comes in, it looks for a worker thread, and it connects itself to this worker. Now it does its work. For example, it creates the request to our endpoint, and then it sends out the request. But as soon as it figures out, okay, I'm blocking currently, so I don't have any, so I have nothing to do, I'm just waiting, it will remove itself from the worker threads and will just put itself onto the heap. So it will remove it from, so that the worker can do other stuff. Now, the cool part is also that as soon as the response comes back from, like, for example, our HTTP endpoint, and the signal comes in from the operating system that the data is available, the virtual thread will tell, hey, I need another worker thread to continue my work. So it will then look for another worker thread which is available. So it doesn't have to be the same, because for us, when we program, when we use this thread, we don't have to care if it's a worker or a virtual thread. These virtual threads are like normal threads in our case, but they are much cheaper to create. Like, they cost only like in the kilobytes, so you can always think of they are like 1,000 times cheaper than a normal thread. So this is why you can create like 1,000 times more threads. So let's create now some threads, and let me show you how this works. So we will go back here in IntelliJ, and we will open our virtual threads test here. Now, we can see here when we started last time 1 million threads, then our code blocked. So let's try this again, but we will change something. We will change this from off platform to off virtual. And we can see here nothing else changed. We still can use the normal thread. It's still a normal thread when you're working with this. So what we will do here is we will call watch count threads from Java. We can see currently 120 threads are running. So let's now start this here. And we will see here that only like 40 threads got created. It's a little bit more, but like these are from IntelliJ because the JUnit needs to run. But we can see here there are only 40 threads for these 1 million virtual threads which got created. So what this means is that it's enough for 1 million threads to only need 40 worker threads to be able to really do their work. Now let's stop this again. And we can see it went back to 122. Now, let's also stop this here. Now, but how does this work? Well, let's change this here up a little bit. And let's say we have if I equals 0. In this case, we have a thread dot current thread, and we output this. And we then have a sleep again of 20 milliseconds. And let's do this 2 more times. So what we do here is we basically say we want to know, okay, what is the current, we want to get the thread which was created first. Then we wait for 20 milliseconds with the thread.sleep, and then we will do this again and again. And let's now run this test. So what we now can see is, when I scroll this up a little bit, we can see here that we have worker 1, which gets, we have this virtual thread 22, which is attached to worker 1 the first time when it gets called. But as soon as this blocks the first time, it disconnects from the worker thread. And what it then does is it looks after 20 milliseconds for another worker thread. And we can see here worker 1, worker 10, and worker 4. But the virtual thread is always still the same. That's important. You don't have to worry about if this is another thread. It's still the same thread. But to make this work, what Java had to do is we can go into let's go into our sleep here, and in this thread sleep method. And we can see here, we can go into this sleep nanos. And when you check earlier versions, like version 17 or even earlier, you will not find this if check here. But what they did is they checking, okay, if the current thread is a virtual thread, then we handle this differently. But they, of course, not only have done it in the sleep nanos, they have done it everywhere in the JDK. So they did like a change with over 100,000 changes in their pull request to change this in the JDK. And it had to be done, of course, in one pull request, because otherwise stuff would not have worked as before. So really crazy that they even tried to do this, and that it really worked that well. So there were no real issues with this. So, but this is how this works basically. Everywhere threads were used, now also virtual threads are supported. So, and now let's go back and migrate our blocking application to use virtual threads. So what we will do now is we will go into our application properties file. And because we're using Spring Boot 3.2 or later, the only thing we have to change is we have to say Spring Threads Virtual Enabled True. And what this will do is it will change, besides some other stuff, it will change the executor service, which is used by Tomcat. So what do I mean with this? Let me show you. Normally when we have Tomcat, we have an executor service which has a thread pool. So we have this thread pool from like around 200 threads, which are at mostly running, and these threads are pooled and not thrown away when they are done. So they are just staying there and are waiting. But now there is this virtual thread per task executor, because these virtual threads, as mentioned, should not be pooled. So each time an executor service creates a new thread or gets called, it creates a new virtual thread. So this is basically what changes, but of course there are some other stuff, but this is like the most important thing which changes. And what we now will do is we will just rerun our application without any changes to our code. And we'll go now back into our JMeter, and we will call our speakers endpoint again, but not the async one, but the one with like we did before, which was blocking. And now the difference, what we will see is that because we are using these virtual threads, we now, as we have enabled them here in our application properties file, the difference now will be that for each of the threads, a virtual thread gets created and not from the connection pool, so there will always be enough threads available. So we can see here we are already done. Let's check the response, and we can see it takes 1 second for all of the requests to finish in this amount of time. So we didn't need to change anything, but just to change the normal threads to virtual threads. And now, this of course is nice and all, but what is here with this example with the talks endpoint? Because as already mentioned, even if this will not block, it will still take 6 seconds, because we have these speakers here, which takes 1 second, and this retrieve talk, which also takes 500 milliseconds per talk. So this is where we could, of course, use parallel stream, but as mentioned, when we have more speakers like 100, this will be much slower. And this is where you can use the structured task scope. Structured task scope basically is like its own executor service, where you can just pass them new tasks, and it will call each of these tasks in its own virtual thread. So we will now use this to rewrite this so that it's as fast as it can be. So how can we do this? The first thing is we create a try with resources block here, and we say we have a scope, and we then create a structured task scope like this. And we say we want to pass to this executor service a talk, or more talks. Like we can pass as many talk requests as we want. Now what we will do is we will wrap this here inside, but of course this is not everything we need to do. We need to change some stuff. So what we now need to do is, I will just remove this here, we will say we have inside of this map, we will use scope.fork, because what this will do is, this allows to pass in a lambda, which then wraps our retrieve talk, because this now will take care of calling this callable in here, but in its own virtual thread, so that it will not block. Now, because of that, of course, we no longer get back a list of talks, but we get back a list of subtasks, which are which are talks like this, and let's call this talk tasks. And we can remove this here. And what this subtask here, this is something we get back from the scope fork. So let's check what the subtask here is. The subtask here is like basically it's an interface which also has an enum in there, and it has a state of unavailable, success, or failed. And unavailable basically is it's still running. Success means it was successful, and failed means that there was an exception or an error happening. The cool part about this is because this is like sequential or like it's not reactive, we can handle these errors really nicely because, for example, we can call here .exception and can then see what the throwable was which got thrown. So, but in our case, of course, what we will do is we think that everything will work fine. So we say here when we have passed everything to our scope we wanted to, we just call scope.join because we want to wait until all these virtual threads we sent were done, either had an error or finished successfully. And we can see here we have a join until to have like a deadline, but we will just use join because we know that it will be fast enough for us. So, and this join, as you have seen, is also throws an exception, so you could also handle this here, of course. Now, the last thing we need to do is we need to say return, and then we have our talk tasks here, and we map over them, and we say subtask.get, because we need to get all the results from this list of subtasks. And now we are done with this, and now let's run our code again, and we'll go back into JMeter, and what we will do here is we will say we have API/talks, and what we now hope to achieve is that this will take only 1.5 seconds, because when we think about what happens here is this will take 1 second, and this scope here we use, this scope fork, will take care of parallelizing all the requests to our speaker, to our talk endpoint. So let's go back into JMeter. We can see here we are done, and let's see the response time graph, and we can see it takes 1.5 seconds because every request to this retrieve talk endpoint was sent by its own virtual thread. Now, maybe you think, well, this now looks strangely similar to this completable future. Yes, it does, and this is why we will rewrite this to make this look much, much better, because the cool part about this is this structured task scope here, we can extend this structured task scope and create our own one. And we will create a really easy one. We have our class here, and let's call this class collection task scope. And we say extends structured task scope, and we pass in this generic. And the cool part about this structured task scope is we have this handle complete function we can override. And this will get called every time a subtask ends, even if it's successful or if there was an issue. So we could now in there, of course, check for its state, and if it's an error, we could pass it to an exception list and so on. But we will make this much, much easier in our case because we know that nothing will fail here. So we will say we have our private final collection of T, and we say this is our queue. And we have to use like a concurrent collection because we are accessing this class from different threads. So we will use a concurrent linked queue. And in this handle complete, we will just say, okay, our queue adds this subtask.get because we will get the result from our subtask, from our retrieve talk. And now the only thing which is missing is how can we access it? So we will have our list of T here, of course, and we say get results. And now what we need to do here, we need to say we have our this.join because we want to make sure, of course, that when we call this get results, that all the tasks are done. So we will just call it like this. And now we say return list copy of queue. And this will now return basically the same as we had in our structured task scope. Now, because of that, we can remove some code here. So what we no longer need is, first, we don't need the structured task scope. We need our collection task scope, which is a talk. Now, what we also don't need is, we don't need this stream list and so on. We can just use scope.getResults. We don't need the scope join here anymore. We also don't need this final list here. We don't need this to list because we don't have to iterate over it. We don't need this to be map stream. We can just use for each because we just pass it to it, and after it we call the scope. And this is already everything we need to make it work again. So we can see here we now have like 4 or 5 lines of code, or like in this case 4 lines of code we had to create to make this use virtual threads. Let's rerun this application and let's see if this is working as expected. Let's go back into JMeter here and do this one more time. Let's run this. And I think we can see here that this is now much easier to understand, in my opinion, than what we did here, because we have just our collection task scope, which can be used, of course, not only for that, but for many different approaches where we have to pass in a list of elements, or we want to retrieve a list of elements. Now we could make this, of course, even shorter by, for example, saying we want to have our own scope.forkAll function, but I think this is much easier to understand. So we are now done here. And let's now see, and we can see it still takes 1.5 seconds. So this still works as expected. So let's, before we go to the conclusion, let's talk a little bit about thread locals, because thread locals basically work the same as before, but the problem which we always have to think about is that thread locals are basically used normally on like a thread pool. So when you use this thread local, every time you create a new thread, then it will add basically a new object to it. And if you don't use remove on your thread locals, then these can get huge, especially with the virtual threads, because like when you create 1 million threads and you create one new thread every time you call have a request, then it can happen that the thread local variable gets huge and you have a memory leak. So first, of course, you always need to use the .remove to remove elements to remove these elements you no longer need. But if you have really expensive objects, take a look into scoped values, because scoped values are like the replacement for thread locals, especially when you use virtual threads. Now some restrictions. First one is synchronized. So when you have synchronized blocks, then you should, of course, only when you have heavy I/O tasks in there, you should replace them with reentrant locks, because synchronized cannot be patched to use virtual threads. And for example, Apache Tomcat had huge problems with synchronized blocks when they switched over to virtual threads, but they just exchanged everything with reentrant locks. So what this means is you can just say new reentrant lock here. This is like a normal Java class, and can then use it to basically achieve the same as you have with synchronized. So, and the next thing which you can't really solve is native calls, because when you have native calls to, for example, C code, then it's possible that they access addresses or memory addresses, and because the virtual threads move itself into the heap, this will get complicated by accessing the memory. So then it will be pinned in the worker thread, and the virtual thread will be pinned together. And the last thing, of course, is when you have CPU-heavy tasks. So when you're doing something where the thread does not block but really does work, then this will, of course, not give any speed improvement, because as long as the thread is busy, it needs a worker thread, and it cannot disconnect itself from the worker. Now, what's the conclusion? I think this is a real alternative to reactive, because it makes it so much easier to create a proof of concept. Because you can simply, even if you have your own framework, you can change your executor service to the virtual thread per task executor, and can then see if your application is still running. And you don't have to rebuild everything from scratch to reactive to see if this really works. The next thing is, it's also done in the JDK. It's not like a third-party library, so you can really just use what's inside the JDK, and there is nothing to build around existing issues with the JDK. And the last thing is also, it's much less boilerplate. So you have simple patterns you can use, like for example with the structured task scope, and they really took their time to think about what could possibly go wrong and fix that beforehand. So yeah, we are currently now at Java 21, and I think we went full circle back from the blocking approach. So that we went from blocking to the reactive, and then we understood that, well, this is a little bit too complicated. And I think with Java 21, we have a real new nice feature in our tool belt to use, so that it's much easier to work with this blocking code without having to change our whole code base. And of course, we don't know what the future will bring, but I think Java 21 really made it easier and is now ready for the future to be used even when you have old applications and you update. So we are almost done. So just a quick, I found this interesting because when I gave this talk earlier this year, sometimes my IDE just froze, the complete computer my complete MacBook just froze, and then later they released such an update of macOS where they said, well, prior to that, the apps that include Java may quit unexpectedly. Now they finally fixed this, so we went through this whole stuff really smoothly, so I really enjoyed that. And now let's see if there are some questions. Maybe not. Yeah, maybe there are some questions in the audience, or just ask me later on LinkedIn or on Twitter if you'd like. Cool. Then, yeah, if you leave, and I think for everyone and for all the other talks, you also will see this today. Please put in some feedback, because it really helps also the conference to see what you liked and what you did not like. Yeah, thanks you for joining, and I wish you an awesome last day at the developer conference. Thank you.